we will see how we can utilize the crystal field theory in various applications. So far we have seen that a particular metal center, if it is present, say nickel 2 plus, and the other species which is around this particular nickel center, it can be our simple water molecules, it can be the hydroxide ion when we get the nickel hydroxides. So, these species basically including the corresponding doubly deprotonated species like the oxide anion. So, these three species as ligand, they can interact with the metal center, giving rise to some complex form which we all know now, that hexaaconical 2 anion or simple nickel hydroxide what we encounter in analytical chemistry, and it is precipitating out also, as well as nickel oxide. So, if we change these environments and if we next compare this nickel 2 ion, say calcium 2 plus or zinc 2 plus, because these two ions without having any d electron in it can interact with these molecules or some other ligand groups in a similar fashion, where they can also interact with the water molecule, they can give rise to the corresponding hydroxides as well as oxides. So, in today's class what we will see that how these interactions are completely different when a particular metal ion have no d electron in its orbitals and when the metal ion has some d electrons in it. So, we will apply basically whatever we have learned so far related to the crystal field theory, where the point charges, we are considering the metal center as the point charge and the ligands are also point charge of negative magnitude or some negative end of the dipolar units which are interacting. So, that particular aspects of this theory, how we can apply to some of our problems related to the interactions of these species or the formation of these species. So, we will see how we can apply this crystal field theory for certain basic energetics of the system and the thermodynamics, how we can control with respect to this crystal field theory, because whatever we get we just one after another, because after calcium we know that we can start the entire first transition series elements from scandium, titanium and all these. So, when we start from filling up all these metal ions with some d electron configuration from d1 to d9, when it is d10 we get the zinc 2 ion. So, due to the presence of these d electrons in the system, their interaction in terms of the corresponding crystal field which is forming around these species. That means, in the solid state, because since these are precipitating out, we can separate it out in the solid state and it has some corresponding structure. So, both nickel hydroxide and nickel oxide can have a solid state structure, where we will see that how this nickel is sitting, whether it is in some octahedral crystal field like that of our hexaaconical 2 ion or in some other form where these ligands have been changed from water to hydroxide ion, or they are forming some polymeric species where this OH group can form bridging interaction with the second metal center. So, that we will see that how we can apply these things and where the energetics for the system or some thermodynamic parameters do vary with the variation of this occupation of these orbitals by the d electrons. So, first of this example would be the corresponding lattice energy parameter. So, what we know that the lattice energy we can calculate out, and applying the Born-Haber cycle, we know that how we can calculate the corresponding energy parameter in terms of the corresponding lattice formation. So, when this metal ion is present, say M2 plus in the gaseous state with some of the species like this oxide anion or say fluoride anion. So, when they are reacting with certain of these anions like O2 minus or F minus, they giving rise to the formation of the corresponding oxide or the fluoride. So, they have certain specific solid state structures also. So, the molecular solids are formed where the interaction between this metal center with that of oxygen or metal center with that of fluorine, how they can vary if we vary this entire series from say calcium to zinc. If the whole thing is dependent on the presence of the d electron in these metal ions, we will see that the interaction with calcium due to the formation of calcium oxide or calcium fluoride, we do not see any effect at the some contribution or the crystal field contribution towards the lattice energy term, that the entire Born-Haber cycle, if we see that there are certain steps to get it back to the complete cyclic process, where the individual steps are involved for some energy values, and one such step we can consider it as the corresponding step where the crystal field can contribute some amount of energy to the entire lattice energy term. So, whether this particular calcium can contribute some amount of this to the lattice energy or the vanadium, chromium, manganese or iron, that means those who are containing some d electrons. And now we all know now, that is very familiar to us now, that whenever some electron is going to these d orbitals, we have the high spin electronic configuration and low spin electronic configurations. If these two configurations can interact with these ions, they are also in the gaseous state, they do interact differently with these anions during the formation of these solid states. We see that some interaction can we have depending upon not only the energy parameter, but also sometimes we can have some important idea about the corresponding metal oxygen and metal fluorine bond distances, because it can not show some linear relationship as we move from left to right, that means beyond the corresponding transition series to the end of the transition series, that we will show some signatures, some indications that crystal field theory and the corresponding crystal field stabilization energy is basically contributing some amount of energy to the entire energy term. So, if we plot, it is a very simple plot, we just simply write it in any fashion. There is a x axis, we will be plotting the corresponding occupancy of the different d levels. So, straight away we can plot from d0, which is calcium, that means we can see the effect of this particular metal ion where we do not have any d electron present in it, to up to zinc where the same situation is prevailing, but the only difference is that here we do not have any d electron in 3D level, but here all the 3D levels are filled, having an electronic configuration of 3D10 to zinc 2 plus. So, in this particular case, like metal oxides or hydroxides or any other solid, chlorides or bromides, the example has been taken for MF2, the metal difluoride of first row transition metal ions. That means like calcium, we can have the vanadium, we can have the chromium, we can have the manganese fluoride, we can have the nickel fluoride, we can have the copper fluoride, and up to we can have the zinc fluoride. So, it is consideration of the corresponding Born-Haber cycle related to the calculation of the lattice energy term for all the fluorides starting from calcium to zinc. So, these 11 elements, if we can consider and if we plot them in this fashion, we will see that the occupation of these d levels do contribute differently towards the lattice energy term for these transition metal ions. So, when we go from D1 to up to D2 to D3, it again drops at D4 and it again come back to the linear straight line. This red dotted line will be related to the corresponding lattice energy increase where we do not have any crystal field contribution. That is why it is falling on a straight line which is monotonically increasing from calcium to manganese, manganese to zinc. That means manganese 2 plus will not show any such contribution towards the lattice energy term, though it is a transition metal ion, but its electronic configuration which is 3d5. If it is in the high spin situation, that means all the 5d orbitals are singly occupied, that means they are evenly distributed for that electronic configuration, and it gives us a corresponding spherically symmetric arrangement. So, like zinc, when all are filled, the manganese will also show no effect in terms of the corresponding crystal field contribution. So, that is why we have the situation for calcium, manganese and zinc, which is monotonically increasing from left to right due to increase in the nuclear charge only, that we have no d electron configuration. This is half filled d level and this is full filled d level. So, after D3, when we go to D4, that means one electron is going to the Eg level, then it is going to contribute less amount of this lattice energy compared to D3 electronic configuration. So, that is why it is less, and D5 is further less than the D4 configuration. Similarly, beyond D8, when it is pairing up, when the situation is completely half filled for manganese 2 plus, the situation is like this calcium 2 plus. So, from here this double hump curve is again forming like this state, that means again 1 electron, 2 electron and 3 electron in the T2G level. Then we have the corresponding one Eg level and the second one is also in the Eg level. So, it is a situation where we are simply considering an octahedral crystal field where all the groups which are coming to attach to the metal ion, but what we are talking in terms of the corresponding manganese fluoride or any other fluoride salt, that we have say manganese fluoride and the solid state packing, the crystal lattice packing, what we have the crystal lattice packing we have to see, and while we determine the corresponding crystal structures, we see that along the different axes of x, y and z and along the A, B, C, we have a typical packing, and that gives rise to us a nice packing diagram for these structures. So, these packing diagrams, what they usually give us the situation that manganese is there, but when it is nicely packed, that means is a typical example for the corresponding crystal field when we are seeing the corresponding crystal structure. This crystal structure gives us the corresponding crystal lattice, and that crystal lattice packing gives us the corresponding packing diagram, where we see that instead of behaving as a simple anionic group, this fluoride anion, the F minus, This F minus is basically behaving as a typical sphere like arrangement. So, it is a solid sphere and we are getting something where we have this manganese which have a symmetric electronic distribution which is also sphere like. So, it is one sphere and we have the other spheres also like this. So, though we have the charge for two fluoride anions, but when it is packed inside the crystal lattice, we will see that all the 6 fluoride anions are packed and within these 6 fluoride groups we can generate some amount of cavity and that cavity can nicely accommodate the corresponding positively charged dicationic species which is manganese 2 plus. So, basically we will be getting in this crystal field diagram and corresponding crystal field packing the cavity what is forming around manganese is giving us a corresponding octahedral crystal field due to these fluoride anions and these fluoride anions are our weak ligands. So, that all we know now, we are now very well accustomed with the idea that when we have the fluoride ligands which are weak ligand, so we will be having high spin fluorides. So, we will be getting the corresponding high spin fluorides because we do not expect any kind of spin pairing. So, this is the thing that when we get these values, so we have a double humped curve. So, we have to be able to justify this double humped curve where we can get these values for these corresponding transitions from calcium to manganese 2 plus to zinc 2 plus. So, we have these fluoride anions which are basically the corresponding weak field ligand and these fluorides are showing us corresponding octahedral geometry for this and we determine these are the corresponding experimental values for the corresponding lattice energy and we plot those lattice energies against the d electron configurations. So, what we get? We get nothing but a double humped curve which we can have is found when lattice energies are plotted against atomic numbers or the number of d electrons. It can be the corresponding atomic number from 20 to 30 or from d0 to d10 if we consider them for a corresponding plot related to the number of d electrons. So, same curve we can have if we just simply consider the corresponding crystal field stabilization energies for all these transition metal ions such as for chromium, such as for nickel. So, if we get this corresponding crystal field stabilization energy for nickel 2 plus which we have calculated in our all previous classes nicely, and if we find out that for weak field if we have a corresponding high field electronic configuration, but nickel 2 plus it will have only the corresponding high spin only or the low spin only which is T2G6 and Eg2 configuration and that crystal field stabilization energy in terms of dq we get the similar type of plot. So, it is nothing but instead of if we consider that whatever amount of lattice energy contribution we are getting for the entire solid structure, but this particular part that means which is above this red dotted line, that means the double humped curve we can also get, since the plot we have not made earlier, we have the calculations in our hand for all the d electron configurations. We have the CFSEs we have calculated so far for both the high spin configuration and the low spin configurations. So, same values in terms of the corresponding dQo, not dQt, because it is not giving us any tetrahedral geometry, it is giving us only the octahedral geometry. So, in that particular octahedral geometry, if we plot these CFSEs, we will be getting the same double humped curve. So, it is only the contribution from the CFSE above this particular line which is directly connecting, where we do not have any contribution for the ions like calcium 2 plus, manganese 2 plus or zinc 2 plus. So, when we see that it can also be applied to the corresponding interaction with that of the metal ion with water molecule, that we have started our discussion, that in the solid state what we have just now seen, that the formation of MnF2. Similarly, we can have the corresponding formation of MnO or MnOH, and this is the corresponding solid state, because in the solid state we are talking about the corresponding LE values, the lattice energy values, but in solution another thermodynamic parameter which is very important when we just see the corresponding interaction, that means the formation of manganese hexa-aco species, where manganese is present in the bivalent state. So, in the solution state what we have these interactions, we get these interactions when we have say solid manganese chloride or manganese nitrate or manganese perchlorate in our hand. So, if we have manganese perchlorate with some water of crystallizations, and this solid we are dissolving in water. So, there will be the corresponding solution and the solvation is also taking place, but what we can measure now, that thermodynamic parameter which will be useful for identifying this particular interaction of the solid manganese perchlorate with water is the corresponding calculation for their hydration. Reaction is our hydration. So, we can calculate the corresponding hydration energy for manganese in +2 oxidation state for accommodating 6 water molecules around this manganese 2 plus. So, it is not for manganese, but it can go like that of our the entire series, because we know that all of them can show some interactions with these water molecules to up to zinc, and also in this side we have the interaction with that of our calcium. So, starting from calcium to zinc, we can see or we can determine the corresponding hydration energy and how this hydration is getting affected due to the presence of the different number of d electrons that we can see. So, from thermodynamic point of view, this hydration energy, what is called this hydration energy? Hydration energy is nothing but the amount of heat energy which can be liberated when 1 mole of gaseous metal ion is dissolved in water. So, the calculations are based on the standard reference of the metal ion in the gaseous state. So, when the metal ion is present in the solution state, it is basically initially hydrated one, then the corresponding heat energy will be liberated due to the dissolution in water. So, that amount of energy we can calculate or we can think of as its corresponding hydration energy, or in terms of the corresponding delta H values, in terms of the corresponding thermodynamic parameter, we call it as a corresponding hydration enthalpy. So, if we look at the change in the corresponding hydration enthalpy values for the different dipositive metal ions in say first transition series elements, where the gaseous M2 plus is reacting with 6 water molecules in the liquid state, giving 6 water molecule connected to the M center, where MH2O whole 6 2 plus, which is in aqueous state, that means which is aquated metal ion. And likewise, that what we have seen just now for the lattice energy, the calcium, manganese and zinc in bivalent states have the corresponding no electron, half filled and full filled d electron configuration, having no contribution in terms of the corresponding CFSE, but the other metal ions do deviate from this extra CFSE gain due to the presence of some odd or even number of d electrons in their orbital. So, that means apart from these metal ions, other metal ions will contribute towards the hydration energy in terms of its CFSE contribution. So, what we see that with the decrease in ionic radii, the hydration energy should increase, because the increased attraction between a small sized cation and a water lone pair. So, cation is very small because it is dipositive, and the water lone pair we can have the corresponding interaction, because the water molecule will face with its negatively charged dipolar end, that means the oxygen ends are facing towards the metal center, and we have manganese or the metal ion to the oxygen interaction, and slowly the corresponding MO bond is forming, and this interaction is increasing as we have the corresponding change in the ionic radii. So, if the ionic radii is decreasing, our hydration energy should be more. So, these hydration energies of the first transition series should increase across the period as the size of the metal ions becomes smaller. So, as the size of the metal ions are getting smaller and smaller, these first transition series hydration energies will therefore increase because of the strong interaction. So, this is one such experimental evidence of LFSE. So, these experimental things that we can determine, we can find it out the actual hydration energies what is there for the corresponding interactions of the metal ions with the water molecules. So, this not only gives us the application of the corresponding crystal field stabilization energy, but it can also gives us corresponding idea about the corresponding experimental evidence of the corresponding stabilization. So, this basically is related to the corresponding size of these metal ions, and we will seeing the corresponding hydration of M2 plus first row ions, and when M2 plus is reacting with H2O giving MH2O whole 6 2 plus. So, these are the very basic things what we can have, that the reaction is the corresponding interactions of the water molecules with the M2 plus, and this gives us some nice clue that whenever this hydration energy contribution is there, that means whenever we dissolve some salt to this species, that means whatever we have in the solution, this is the starting point for the complexation reaction, and when we add certain ligands to it, if they are 6 in number, then this manganese can form the corresponding MnL6 species. If the ligands are neutral, it will have 2 positive charge, and whatever number of perchlorate ions, anions are liberated, that will now come and go for the corresponding charge neutralization, and will be ending up with the corresponding MnL6 perchlorate salt. So, we will have the corresponding Ml6 perchlorate salt. So, we will have all sorts of other contributions afterwards, that means whenever we are forming the corresponding metal complex, depending upon the corresponding crystal field strength of the ligand system, we can have the different magnitudes of these crystal field splitting or crystal field strain, and their corresponding CFSE values for this particular ligand. But the corresponding energy contributions or the energy term due to the formation of the first step, that means the corresponding ACO complex formation, most of the time we are neglecting that. So, if it has very high energy contribution towards the formation of these species, what we will find that due to this high energy contribution, and if the energy contribution towards the corresponding crystal field stabilization due to the presence of the L group or the second step of interaction, it may not possible all the time to substitute all the 6 water molecules from the coordination sphere. Instead, we can have certain species like these, that where we can substitute 4 of these water molecules by L, but 2 water molecules are still remaining there. So, these are the other possibilities for stepwise removal of these water molecules by 6 L groups one after another. That is why we get the different values of the corresponding stability constant. So, that is another thermodynamic parameter or thermodynamic energy contributions towards the formation of complex formations. And these different steps we will again see when we will talk about the corresponding reaction mechanisms for the formation of these complexes and their corresponding energy contributions. So, this particular interaction with 6 water molecules towards this M2 plus species is the most vital and most important interaction in coordination chemistry. So, when we see these heats of hydration again, and these heats of hydrations again show 2 harms or double harms, again consistent with the expected CFSE of the metal ions. The values for D5 and D10 are the same as expected with the CFSE equal to 0. That means they again form like that of our lattice energy, they again form in the straight line, and the linearity is preserved with respect to the D0 with D5 and D10. So, again we can directly write down the double humped curve, which is very much similar to that of our lattice energy, but this energy axis is only different. It is the delta hydration H0 in millijoule per mole, and this particular values for this contribution is that we have the error bar also depending upon the measurements and depending upon the salts used. But the monotonic increase of these values for this green line, which is showing that D0 to D5 to D10, and if we just go for these contributions for the CFSE, we will be having these orange lines for this double hump curve. But if we do not get the corresponding CFSE contribution, all these values will come and will fall on the green line where we do not have any CFSE contribution for hydration. So, what we see that it also predicts a smooth change as nuclear charge increases and size decreases. So, monotonically it is also increasing, the hydration energy values are increasing as we go for increasing the nuclear charge, and nuclear charge is responsible for squeezing the size of the metal ion, and the size is decreasing, and we are having more and more interaction with the M2 plus center with that of our H2O molecule. So, as we move for M2 plus, as the size decreases, this interaction with the lone pair of electrons, the lone pair of electrons on this water. So, this particular interaction is basically increasing. So, as the nuclear charge is increasing, the size is decreasing. So, there will be a change in the corresponding interaction. and if altogether 6 such bonds are forming. So, it can be multiplied by 6 when the metal center is interacting at the same time almost with 6 water molecules for their contribution towards the hydration energy. So, this basically tells us that how we can magnify the thing and how we can have these values for these contributions, where H2O is again like that of our fluoride is a weak field ligand. So, if water is considered as the corresponding weak field ligand for these metal ions, we are getting the corresponding values for the high spin configurations only, and we do not have to bother about the corresponding low spin electronic configuration. And the enthalpy, the delta H becomes more favorable, more and more favorable left to right, because we are getting is in the negative end of this enthalpy, the hydration enthalpy on the negative side. So, we will be gaining for this hydration or this solvation of this transition metal ions. So, solvation or the hydration of this transition metal ions is basically energy efficient process, and immediately when the metal salt is dissolved in water, it immediately goes for its hydration reaction. Then we will see the third parameter. The first what we have seen is the lattice energy, then hydration energy, and for all these cases one particular parameter which is involved is the corresponding ionic radius. So, how this ionic radius do contribute towards these two energy parameters? What we have seen that for the corresponding lattice energy and corresponding hydration energies. So, definitely the ionic radius is changing with the change in d electron configurations. So, this contribution, that means what we see that the corresponding effect what we see in terms of the corresponding crystal field, that ionic radius will also change with the change in the d electron configuration, and that particular change also can interact for the different types of the solid phase anions or the water molecule for their corresponding energy change due to lattice formation and hydration. So, for a particular oxidation state, the ionic radius decreases steadily on going from left to right in a transition metal series. So, we see that this is the case, and we see a monotonic contraction in the size. So, ionic radius is falling because in other two cases the energy parameter what is changing for the hydration as well as corresponding lattice formation, it is basically increasing from left to right, and the main effect for this corresponding contribution is in one case that if there is no contribution for the d electron occupancy, we will have a monotonic decrease from calcium to zinc as the nuclear charge is increasing, which is squeezing the corresponding size, and we are having a corresponding ionic radii from 113 or 114 picometer to say here it is almost 80 picometer. So, in this range basically 114 picometer to 18 picometer, the whole thing is basically again showing a double humped curve or in the reverse direction, and the ionic radii will also be changing with the change in the number of d electrons which are present in the two levels, that means the T2G level and the EG level. Why this is so? Because the occupancy in these two levels where we have the T2G and EG electron, and if we have an octahedral crystal field, what we see that there are orbitals which are T2G and EG. So, this T2G set are intermediate between the two ligands. So, if the ligands are facing directly from x, y and z direction, the orbitals are being placed between x and y, between y and z and between z and x. So, these are basically of different direction, but these are basically facing the ligand direction. So, if we are talking in terms of the corresponding interaction with oxygen of the hydroxide ion, if it is metal hydroxide formation, or if it is hydration for the water molecule, we will be seeing different effect for this particular p orbital, which is facing the corresponding lone pair of electrons from the oxygen atom of the corresponding electrons in the d levels of the metal center. So, if it is in the xy direction, our orbital will be like this. So, it is not directly facing the corresponding oxygen p orbital. So, this is our T2G set, but when this metal oxygen is there and we find this corresponding direct face of these orbitals, and if they are empty it will face differently, if they are filled it will fill in a different way. So, this is the corresponding thing in x and y direction. So, if we have the orbital in x square minus y square direction, so we label it as EG. So, the difference in the electronic configuration in the T2G level and the EG level will definitely contribute differently towards the corresponding ionic radii values for these metal ions. So, what happens if an EG electron is there, that EG electron will try to increase the MO bond length, which is quite obvious, because this metal ion having EG electron facing the ligand orbital, the ligand p orbital or any other hybrid orbital directly. So, there is head to head overlap, head on overlap between metal d orbital and the ligand p orbital. As a result, the corresponding metal oxygen bond length will increase. But if the electron is in the T2G level, which level is in between the metal oxygen axis, and that will have a different effect or rather opposite effect, and that will basically decrease the corresponding metal oxygen bond length. So, occupancy for this T2G level, that means here up to this, up to vanadium 2 plus, will decrease the corresponding contribution for the MO bond length. That means it will have its corresponding share, the M will have its share for its ionic radius and oxygen will have is for anionic radius, because if we add up these two, then only we get the corresponding metal oxygen bond length. So, as this particular bond is decreasing, we are also getting a decreased value for say vanadium 2 plus, but when we move from vanadium 2 plus to chromium 2 plus, we put one extra electron in the EG level in the high spin configuration, and in that configuration the EG electron goes to the chromium 2 plus for D4 electronic configuration, and that basically will increase the corresponding MO bond length, and this particular change will also contribute towards the corresponding increase in the ionic radius of chromium 2 plus. So, same thing also happens that there is a monotonic decrease from manganese, which is in the green line, green dotted line, for iron, cobalt and nickel, but again when EG occupancy is there for copper 2 and zinc 2, this is EG3 and this is EG4, we again lose the corresponding contribution towards the corresponding crystal field stabilization. So, depending upon the different electronic configuration with regard to the T2G occupancy and EG occupancy, we have a steady variation in the corresponding ionic radii as we move from a D0 system to a D10 system. So, when this is we are getting the same thing also we can have if we have large number of these metal complexes where it can bound to the metal hydroxide system or metal oxygen from other phenolate donor ligand or the metal water distances. We can plot them against the corresponding atomic number of this or the corresponding d electron occupancy. We get the similar type of plot for these MO distances at the same time. So, these variation in these ionic radii can also be reflected for these two types of cations. One is the bivalent and another is the trivalent state, and we see for the low spin and high spin case also we will have the different type of things. So, this is one type of thing. So, it was the corresponding dotted line. So, if we move from here to here it is one hump and here to there it is another hump. Similarly, here also we have the hump up to manganese. So, this is manganese one hump and then we have another hump for the rest. And so far we were considering for the system bound to either fluoride anion or hydroxide anion or the water molecule. That means, they are giving us only weak field crystal field. As a result, we have only the high spin electronic configuration. So, if we just go for the corresponding low spin electronic configuration, we do expect that straightaway it is go down up to iron 2 plus, which is T2G6 electronic configuration. That means, straightaway we go up to T2G6. Similarly, for trivalent also we can go down to this particular case, which is cobalt 3 plus, which is 3D6, and as a result in the low spin electronic configuration this is corresponding 3D6 or T2G6 electronic configuration. So, in case of iron it is the bivalent case, and in case of trivalent state it is the cobalt 3 plus having full occupancy. Here it is half occupancy, full occupancy of the corresponding T2G set, and this particular case it is basically going decreasing steadily up to this configuration of T2G6. Then again it will increase for nickel, it will increase for the nickel, zinc and all these things. And if we just plot, because not all examples of trivalent state we can have, we can go up to gallium from scandium 3 plus, because the scandium should be the first entry for the trivalent metal ions, because we do not have anything corresponding to calcium 2 plus or the corresponding vanadium 2 scandium 2 plus is there. So, scandium 3 plus to gallium 3 plus, again we will see simply not a double humped curve. For the low spin case we have a V shaped curve only, straight down over here then go up, straight down over here and then again go up. So, for the low spin case there is a steady decrease up to the corresponding configuration of T2G6, and after that we increase from T2G6 to EG1. That means, the next one is this one, which is nickel 3 plus, which is 3D7, and for the copper one also in plus 3 oxidation state. In case of high spin also the change is very steady from one step to another, but there is an increase once the T2G cell is half filled. So, after T2G3, basically after this particular state, that where we have this one, this up to the vanadium 2 plus, which is the T2G3 case, then we have the chromium and manganese. Then once we go for the chromium state, it is basically increasing from chromium 2 plus, and for the manganese 3 plus, which is also D4, that means here it is again increasing. So, in case of bivalent state it is chromium 2 plus, in case of trivalent case it is manganese 3 plus. So, depending upon only the electronic configuration we can see the same effect for manganese 2 plus in high spin and for the corresponding chromium 2 plus in the corresponding high spin case. Then we see some useful information related to some solid state structure which has a different name, what we call as the corresponding spinels. So, these spinels are basically mixed oxides. So, how we treat these mixed oxides with regard to the corresponding preference for their sites, and basically we will be talking about the corresponding preference of these mixed oxides. That means, we have metal ion M1 and metal ion M2. So, where M1 will be there and where M2 will be there. But before that, when we are talking about the corresponding lattice energy, the lattice energy values, we have seen that the typical spheres were available, and if we have the close packing of these spheres, so this is one layer, which is the first layer, and next if we have these red circles as the second layer, these are the second layer. So, what is happening due to that is, whenever we are having a close packing of these spheres, because these spheres can be simple HO minus, F minus or O2 minus. So, this is very much similar to that of a particular metal complex, what is forming, say manganese is forming. So, we have one layer of ligands, then we have manganese, then another layer of ligands. So, if we have here, that means manganese is bound to several of these water molecules, these are all water molecules, and like these things, that means the green circles, these green circles are showing a triangular arrangement. So, we have a green triangle. So, if we take the center of these green circles and add up, we have a circle like this. Then if we just consider the center of the red circles, the center of the red circles will be like this. So, this particular feature we can have if we take 6 spheres together, and the center of all these 6 spheres are taken in this particular diagram. So, here what we see that in this particular case what we have, so these 3 are in one layer, that means the first layer, and these 3 are also forming another layer, which is our second layer. So, if these 2 layers are sandwiching a particular small sphere, which is small in size, that means we have a sandwich structure of one layer and second layer. Between these 2 layers, we have the trapped metal ion, which is a very small one and which is basically sitting inside nicely in an octahedral geometry. So, in this particular octahedral geometry, what we find, the same geometry we can have if we have a close packing of spheres. So, if we have close packed spheres in the solid state. So, whatever thing we are discussing here is based on the corresponding solid state structure. So, in the solid state structure, of these hydroxides, of these fluorides and all, we have the closed packed spheres, and these two layers are basically forming either from hydroxide ion or the fluoride ion or the oxide ion. But at the end what is happening, that we are generating something, this small space. This small space is nothing but the corresponding equivalent position of this manganese. So, due to this close packing of spheres, we have generated one octahedral hole. So, that octahedral hole we have generated, and within that particular octahedral hole, now we can put any metal ion, say this manganese also. So, this gives rise to the corresponding spinel structure, and how the spinel structure can also be controlled due to the corresponding energy calculations in terms of the corresponding stabilization due to the crystal field. That we will see in our next class. Thank you very much.